distributed, so we are kind of okay-ish set up for this new world where everything is virtual. Though I do still miss conferences and having the experience in person, unfortunately. But it is the best that we have this year. I hope next year will be different again. So what I want to show you is generally 3 topics or areas. So we have lifecycle management, then frozen indices, or generally what we call the cold tier nowadays, and then roll-ups of your data. So these are the 3 topics that I will show you hands-on. First off, we start a demo, which is always a good reminder. Normally, I would be running this on my laptop with Docker Compose, but since we're running Zoom and screen share, which normally eats all my CPU, I have put that on a virtual server. So I want to run sudo docker compose up. This will just set up a 3-node Elasticsearch cluster where we will be able to see how it scales and how data moves through it. And I will let that set itself up. So this started from 0. There were no Elasticsearch nodes, no nothing. This is fully automated. I will show you a bit what I'm doing in the background, but let me get started what I'm actually doing or showing you first. So lifecycle management. This is generally the part if you have lots of data coming in and it's some data that has a timestamp. It's normally something like your logs, your metrics, maybe traces, anything that has a timestamp and then has a life cycle. Because normally you collect all the logs from today and then you keep them for amount X, but after that you delete the data. So the idea of lifecycle management is very much like data comes in, today it's very relevant. Then maybe it's not so relevant a week later anymore because you will probably most likely look at the errors from today or yesterday. The older data you start searching less frequently. So you might be able to move some of the older data to slower nodes because you don't access it that frequently, and you might be okay to have a bit more waiting time to get a response back. And then after some time, you probably want to delete data. The question is always like, how long do you want to keep the data until you delete it? Normally, when you start the discussion, people will always say like 100 days because it's the first thing they can think of, or a year. And then you say, okay, this is what it will cost you in hardware. And then they will say, okay, 10 days or 15 days or whatever is fine as well. And lifecycle management is really the idea to allow you to remove the data once you don't need it anymore, but also to move it to different types of hardware to keep your costs at bay, basically. So that's the general idea of what you want to do with lifecycle management. First off, index lifecycle management. So all the data in Elasticsearch that we store is stored in something called an index. It's roughly like a table or so in a relational database, but not really. It's just like some data that is related to each other. For example, all your logs might end up in one index. And what I have in terms of icons below that is what we call the different stages of these life cycles. So this is hot, warm, cold, and then delete. I used to have a skull here for the delete phase, but then people said it's too unfriendly, so we're sticking to the garbage can for the delete phase. So hot is generally your data comes in, you need to store it. So this is where all your write operations happen because all your logs come in with the today's index, for example. So this is where you write them. Then after some time, you move the data to the warm phase. The warm phase is basically, it's read-only, and it's more or less frequently searched. It might be 2 or 3 days old. So stuff that you don't always access and where you're okay to wait a bit longer. And then you might have a cold phase. And the cold phase might be something that you search very infrequently. For example, some security logs, you might only look at or you might have to look 3 months back or so. And you will be okay to wait longer on those, but you don't want to spend a fortune on having lots of expensive nodes to sit around idly just to wait for that infrequent search. So here you just want to have more density per node. So you store a lot of data there, and you can access it if needed, but it might take some more time. So this is kind of what you want to have. So from hot to warm to cold, and at the end, the data will be deleted. And that is what we call index lifecycle management. And these are the actions in Elasticsearch, how you can actually implement it. So that is pretty deeply hidden in our code. And this is just like the relevant lines from that Java class that I have taken out. Doesn't even look much like Java. It's about like you have an ordered action for the different phases. Like I said, hot, warm, cold, and delete. So these are the different life cycle stages that you can run through. And then you have these individual steps. And let me give you a quick overview of what those steps are. So first off, you can set a priority, which is not very important. It's mostly like if a node restarts, it's like which indices should be accessible first. Normally, you want to have a higher priority on like the hot data because that's what you want to access first. But otherwise, all the phases have this set priority phase, but that's one of the less relevant ones. We have unfollow. This would be if you replicate the data to another remote cluster. Also not that common, so in most cases you won't have that. What you could, or what you will have is you will have a rollover action. A rollover action is basically when do you want to create another index with data. And like since we have a time-based approach, you don't want to store everything into a single index because that will just keep growing without bounds. And then deleting anything from that index is relatively expensive. The way that Elasticsearch and Apache Lucene stores its data is immutable. So what would happen is you would have to delete the documents, but you would actually only mark them as deleted. And then you would basically need to merge all the pieces of data that are around to actually get rid of that because it's an immutable data structure. And that is pretty expensive. So you generally don't want to have that you delete lots of data from an index. What you would rather have is you would create another index and then delete all indices altogether. So the previous approach was to use a daily index pattern, which when you think about it, makes a lot of sense. Like you write today's data, and then it's just like moving through different stages in your cluster. And after, let's say, 30 days, you delete all your data because you don't need it anymore. But the problem is that, especially with logs, for example, your data might be, or the amount of logs might be very unevenly spaced out between the days. So you might have Monday is today, so you might have a lot of logs today, but the last 2 days on the weekend, you might have had very few logs. So what you would get with a daily index pattern potentially is that you would have like very unevenly sized indices, which is not great for Elasticsearch and how it handles data. What you would have ideally would be indices that are more or less evenly sized. So what this rollover action does basically is you can define a condition which can have one of 3 actions of when to create a new index. It could be time-based, so it could be daily, but you could also say like every 6 hours. That's often not ideal because it might still give you unevenly spaced indices. But you can also say the number of documents or the size of the index. Once you hit that, you want to create another index. So the default setting that we have is in many configurations that we provide that after 50 gigabytes of data being written, we would roll over to the next index. So it would always create you chunks of indices or different indices of approximately 50 gigs or in size. This is what your rollover action can do. Also, it could force merge the data here on that hot node. Which basically means it optimizes the index structure internally. You could also force merge on the cold node afterwards. Normally you would do it on either one of these. You can do, because this is a pretty expensive operation, you could decide like, do I want to do it on the hot node? Might have more power. Or you could do that at the end on the warm node, but the warm node might be too busy with other stuff, or the hot node might be too busy with other stuff. So that's why you can pick where you want to do this optimization step, basically. On the warm node, you have a lot of the similar actions. So you have the priority again, you have the unfollow. Here you set the data to read only. So The assumption is that on the warm node, all your data is in read-only mode because you're not going to add many logs to yesterday or the day before's logs anymore. Those have already been processed. So this is just another optimization to speed things up and also to provide some safeguards that this is read-only. We have an allocate action, and the allocate action is basically how we move the data from a hot node to a warm node. What I will show you soon is that our nodes have different tags. And based on this allocation, you can say like move data from this hot node to the warm node. You can do a shrink, like this is also again the data structure in the background. You can reduce some overhead that was important to parallelize when writing all of it, but it might not be necessary when you actually just read the data. And that's it for the warm node. On the cold node or cold data tier, you have again priority, unfollow. You have again the allocate. So now you would move the data from warm to the cold node. We have an action that is so-called freeze. What freeze does is it makes your data like almost dormant, so it takes fewer resources, but you can still search it. And then we have a concept called searchable snapshots, which is not implemented yet, but will come soon. That will make your data searchable actually on Amazon S3 or any other blob storage. But that's a bit more things to come, and I will only briefly touch on that. And then finally, you have the delete action, and the delete action obviously has a delete, and it also has a wait for snapshot. And the wait for snapshot is basically take a backup of the data before finally deleting or removing it. Also makes sense, I guess. So these are a lot of steps that you can run through here. Not all of them are super relevant, and I will show you a configuration of how I want to apply that. Let me jump to my configuration and let me find my config, or actually no. I'll show you the live object. So what I have this folder checked out. So this is using Docker Compose. This is the entire setup, and I will share the Git repository afterwards, so you could try out all of that yourself. So where I'm starting is we have this Docker Compose file, and in the Docker Compose file, we have 3 Elasticsearch nodes defined: hot, warm, and cold. This is probably no surprise because these are also the life cycles that we have defined. What I'm doing here basically is I am creating this Elasticsearch node based on the base image, and I'm making 1 or 2 small modifications that are not super relevant here. What is relevant here is I have this attribute, the node attribute size, and it's set hot. So this defines this is the hot node. And then this will start the node with this attribute, and then I know when I put all my or store all my data, it will go to that hot node. Also, I have some other settings, like I give this instance half a gig of heap memory, and I tell it these are the other nodes in my cluster. And hopefully in the background while I'm talking, all of those form one big cluster, and we'll start working on data together. I also set some limits, so this container is limited to 1 GB of memory, and it uses the default port. Next up, pretty much the same thing, but the warm node. The main difference is that the size attribute is warm here. So this simulates the warm node. Next up, again, no surprise, the cold node with the attribute cold. So this will make sure that this node gets all the cold data. And then finally, I have Kibana, which is like the window into all of this to make interaction easier, and we don't have to fall back to plain JSON. This can just talk to any of those 3 nodes, and that's it. And then I also have a short-lived container to actually configure all of that. And I can show you some more of those configurations. Oh, and finally, I have one beat, which is like a lightweight agent. This just collects the system metrics of this host. And this is actually the data that I'm storing to show you that is how data is coming in and is being processed through that pipeline for you. So this is the setup in Docker Compose. So we have 3 Elasticsearch nodes: hot, warm, cold. We throw data into it, and it moves from the hot to the warm to the cold node and is being deleted at the end, which should have already started in the background while I'm talking. Like here, you should see things scrolling by, so you can see the Elasticsearch cold node is doing some SLM. This is the snapshot lifecycle management cleanup. So this is what it's doing in the background. If there are any questions, just shout and I'll try to answer as we go along. So I've shown you kind of like the Docker setup. Obviously in production, you would want to run this on different physical nodes and also probably have different hardware profiles. Like the hot node might have more CPU and memory because it's doing all the write operations. The warm and the cold nodes might have more storage, so they can just store more data, but they will not have that many search operations and they don't have any write operations. To keep it simple, I'm running everything locally here, and you can just clone the repository, and when you run a Docker Compose up, it will set up everything for you in just work. What might be also interesting is in this setup folder, I have various pieces of information of how this is all configured. And what I should probably show you is the ILM JSON. So this is the index lifecycle management policy JSON file. So we have ILM JSON. And this is what I have configured here. This is using demo values. You should not, so I see there is a question about licenses. Everything that I'm showing you here is free to use. You can just download all of that and go wild. The one exception will probably be the searchable snapshots, but since this is not out yet, I don't want to talk too much about the license yet because we haven't even announced any licenses there yet. But everything that I'm showing you right now is available for free. You can just download that and use that. Thanks for the question, Gregor. So what have I configured here? These are demo values. These are not good values if you want to run anything in production. Because what I'm doing here is I'm defining the rollover phase at 5 minutes or 5 megabytes. So whatever happens first, I want to create a new index. Why these very small values? They're much too small for production. But since this is a demo, I want to show you stuff moving around in the background. So that's why I roll over so quickly. 50 gigabytes would be a better value for this normally. And then you can see after that, 5 minutes after that rollover happened, I will move that data into the warm stage, and then I will make it read-only. I will allocate it to a warm node. I will have or keep 0 replicas. I will do a force merge. This is just an optimization of the internal index structure. I will reduce the number of shards. This is basically the pieces of what this is made up in the background to 1. And then after 10 more minutes, I will move this to the cold phase where I allocate it to the cold node and I freeze it. I will talk about freezing a bit more later on. And finally, 20 minutes after the rollover, I want to create a snapshot, and I'm creating a new snapshot every 10 minutes. And after that, I delete my data. So 20 minutes after the rollover, so like 30 minutes or so after ingesting the data, everything should be gone again. Again, these are only demo values. This doesn't make any sense for production. But this is what I have set up here. So these are the different pieces that I have configured here. Maybe one thing that I should point out as well for the demo. Normally, these policies run less frequently. I think like every 1 or 10 minutes would the index lifecycle management policy run. But since I want to show you stuff moving around quickly, I have changed these schedules to be very frequent, which cause more overhead on the cluster. But it would, of course, make sense in our demo to see stuff happening quickly. Normally, these will be a bit more conservative just because you will only roll over once a day or every 50 gigs of data, and you won't have 50 gigs of data after 5 seconds probably. Otherwise, you will need a lot of different settings as well to make this work better. Okay. final piece, how is this all tied together? How does my data know that it should go to a hot node initially? We have a template. So we have a template called template metric beat. In this template, I define that the data that I'm writing, the metrics that I'm collecting, should have two primary shards. So this is like a data structure that you could split over two physical servers then if you wanted to. It should be allocated on the hot node, and it will use this lifecycle policy that I've just shown you that is called metric beat. So this is basically the template that is being used when I write any data, and that will make sure that my data goes to that hot node and uses that ILM policy that I've shown you. How can we combine this additional warm cold nodes with existing infrastructure which already has a platinum license? Again, a question from Gregor, thanks. So the thing is, one cluster always needs to have one single policy or license. So all your nodes within that cluster would need to have a platinum license. But since everything I'm showing you is freely available, you could just apply those features that I'm showing you within your platinum license. Platinum will, of course, include all those features. It has a lot of more things that I'm not showing you here, but you can just use the ILM policies within your cluster. But all your nodes within one single cluster would need to have the same license. And hot and warm, the license wouldn't change on those. The only thing is you would basically tag your existing nodes with either hot, warm, or cold, and then you could move data between them. And like I said, you might have different hardware profiles for them, so that you might have more memory and CPU on the hot node, and then might have more storage on the warm or the cold node, because they have like different profiles in access patterns. So you could optimize the underlying hardware or just the amount of data that you store there. I hope that answers the question. Otherwise, shout and I'll try to come back to you. Next up, I hope whatever I have been running in the background here has actually worked. So let me refresh my Kibana. You won't be able to access that. I haven't set up a password, but I have restricted the firewall. So this should only allow me to access this cluster. So while I have been talking, we have multiple indices here coming in. So what we had first was an index called metric beat dash and then all zeros. And this is then creating up to 5 megabytes of data or 5 minutes of data, whatever comes first. And then it creates a metric beat dash 00001, 2, 3, 4, etc. So you can see 4, this is the one which we are currently writing to. And then you can see we have this shrink one, because here we have changed the number of primary shards from 2 to 1, so we have shrunken it down. So these two here are in the warm phase. This one here is, these are in the hot phase. This one here is in the warm phase, and these two are frozen, so these are in the cold phase already. And 10 minutes or so, this one will be deleted, and then this one, etc. So data comes in, gets a new number, so metric beat dash 000 whatever, so this will just keep getting up, and then the data will move from the hot node to the warm node, will be shrunken down in terms of primary shards, move to the warm node, then it will be moved to the cold node, and will be frozen. I can also show you how my policy looks like in the UI. So you can see we have metric beat is the name of that ILM policy that I have created. And this is just showing you what I have shown in the JSON file. So the JSON file is what I was using in this kind of the truth, but you can also click this together or check what is configured in the UI in Kibana here. So you can see after 5 megabytes or 5 minutes, whatever comes first, you roll over. In the warm phase, after 5 minutes after the rollover, you actually move this to the warm node, which is not properly shown here, but this should show you this is moved to the warm node. It will shrink down the number of primary shards to 1 from 2 to 1. It does a force merge. Then 10 minutes after the rollover, it is being moved to the cold phase and allocated to the cold node. It freezes the index, and then 20 minutes after the rollover, it will delete this data and take a snapshot right before that. And this is everything that I've shown you in the JSON file. This is just a UI version of that. So, just one thing about that timing. When you have time-based indices, that's the age of the index. When you use rollover, it's the time from that rollover happening. And one thing that sometimes people ask is like, can one phase overtake the next? So if I would configure it wrongly or so, no, it cannot. Like the cold phase will only run once the warm phase has finished. So the cold phase could not overtake the warm phase. Wouldn't make any sense otherwise anyway, but I'm just saying like one phase cannot overtake the next. Yes, Mitya, that is a great question about Curator, which is actually my next slide. So for those who don't know Elastic Curator, Curator is a piece of software written in Python running standalone, which has like two downsides. First, it's an independent piece of software running outside of the cluster. And if that crashes, it will just not run, and then your cluster might overflow at some point if you don't frequently check it. The second thing is we have our cloud service, Elastic Cloud, and we don't provide Curator there. And then you would need to use our cloud service and run on your own server again, Curator, to actually take care of your data. That's why we created ILM. So Index Lifecycle Management is like the, let's say the 20% complexity, but 80% feature set of Curator. And it runs as part of the Elasticsearch cluster. This is the big advantage. It is part of the cluster, so you don't need to take care of that anywhere else. Curator is still around and will be around for quite a while because it has more features. If you have any complex setup around more complex snapshots, around complex alias setups, if you want to have more fine-grained control over only use steps when, I don't know, at night, because then my cluster is not so busy. Those are all things that ILM cannot do and probably will not do anytime soon, because it's trying to focus on the generic use case and cover a lot of ground without adding a lot of the complexity. So Curator is still there, it's maintained, you can use it, you might not need it anymore. ILM might just be simpler. But it's a great question. It comes up pretty much every time. If you have a Curator setup that works and you're happy, keep using it. We are not forcing you to migrate, but ILM is the thing where we are most heavily investing going forward as well. So ILM is kind of like, if you can use ILM, use ILM. If you have an existing Curator setup or need a feature that is only available in Curator, use that. I hope that answers the question for that. Okay, next up, since I called this entire section lifecycle management, how are we doing time-wise? Okay, we still have time. Snapshot lifecycle management is, unlike managing indices, manages snapshots, which is not super surprising. So let me just show you, I'll just show you in the UI to make this simple. There's also a JSON file, but you will have to believe me that this has been generated from this. So what I have is, I have a repository, which is just a shared file system. So all my nodes can access that. And then I have a policy, and the policy basically says I create a snapshot every 10 minutes, which is pretty obvious from the name. And you can see it's just Tron syntax. So every 10 minutes, we will create a new snapshot of all the data that is there. And then I have a retention. So I can say only keep 30 minutes old snapshots, again, very much a demo value. Keep at least 2 snapshots, but keep at most 5 and delete them after 30 minutes. So that is the general idea, just create snapshots of the current data, but throw away the old ones because they might just create a lot of data that you don't need. And in the history, you can see the last successful snapshot was just run 7 minutes ago. So in 3 or so minutes, the next one should run. And in the snapshots, you can see this, and this has a more or less readable timestamp. You can see at 8:10 and 8:20, my snapshots have run, and at 8:30, the next one will run. And you can see the one at 8:10 only had 13 indices that we have backed up, and this one already had 16. So you could click on that, and it would show you these are all the indices that we have, and 6 more that we have taken a snapshot of, and how long it took, and if anything failed, etc. This is just another curated way to run your snapshots. I skip over that because it's probably going into too much detail. It's one of the nice performance improvements if you're not actively searching your data, but it's probably going too far for now. Next up, the so-called cold storage. The cold storage is generally what you want to keep around. Sometimes it's the compliance layer, where for compliance reasons you need to keep your data around for a year or 3 years or whatever. Or it's just because you have so much data and you know it will be accessed very infrequently, like maybe your security team needs to look a year back into the past if some specific event happened, but you don't access it very frequently. So you want to store your data there relatively cheaply without breaking the bank. So what you generally have is, or what is expensive on your nodes is, disk is not that expensive. Normally it's CPU and memory. And since it's Java, it often uses a bit of heap. And what you want to have is you want to have a better ratio from heap to the storage. So you want to have denser storage. And you have 3 different sizes or layers here. You have a regular index where you can write and read quickly. You have a frozen index. A frozen index is like one that is almost not accessible, but it will be made accessible on demand. And then the closed index is something that is just sitting on disk and you cannot actively search it. You would need to explicitly open it. So it loads some data structures into memory, then you can search it again, and then you could close it manually again. A frozen index is kind of the middle ground between them. You can search it and it will be opened up on demand, searched, and then closed down more or less, as a rough approximation. What is nice about these frozen indices is, or the preconditions are, they're read-only, unsurprisingly, and they generally need no memory or very little memory if you don't actively access them right now. So they are mostly sitting just on disk, waiting until you access them. They have a dedicated thread pool, which is pretty conservative. So we will only run one search operation for a closed index at a time. By default, you could change that. And we would only queue 100 requests for them. Otherwise, we would reject requests. So basically what this does is all your closed indices are sitting on disk. And then you would search them, and then you would go into the first index and open it up, search it, close it down again, go to the next one, open it up, search it, more or less implicitly close it down again, go into the next frozen index and search that one. So it would just do one frozen index operation at a time. Let me give you a quick demo of how this is supposed to look like. We don't need this. We want to head over to the DevTools. And I have magically copied this in already. Let me make this slightly larger. I hope this is large enough for you to see. So what I want to create here is I create an index called frozen. The frozen index is allocated on the cold node because that's where I put all my frozen indices, and it has 0 replicas. All good. Right now, it's a regular index. So I'm storing 2 documents, one document with the name Philipp and one document with the name Nicola I store there. And I can just search that because right now, even though the index is called frozen, it's a regular index. You can search it. You can see these are the results that are coming back from this. Now, before freezing it, what you want to do is you want to optimize the index structure, this force merge. You've seen that in the ILM policy before already. So I'm force merging that. So it's an optimized index structure. And now I freeze the frozen index. That's a great naming pattern we can discuss, but that's what I have called it. So I have frozen the frozen index. So underscore freeze freezes it. Now, any guesses what happens when I try to search this index? And this is probably surprising because when I run this, you don't get back this index doesn't exist. You also don't get any documents back. You just don't get anything back, which is pretty surprising. But this is like for your protection because it's potentially expensive to search a frozen index. You need to pass a specific parameter, at least in version 7, ignore throttled false. So you want to ignore this throttle thing. Then when you pass or add this parameter, then it will actually search your index and then you're getting your 2 documents back again. So only if you ignore that index or that setting here, then your frozen indices will be searched. You could also look at like the settings of that index. So you can see it's a frozen, the index is called frozen, has 1 primary shard, has 2 documents, needs 4 kilobytes or whatever on disk. And it's generally open, which is maybe confusing because we didn't call this frozen, but this is still called open. Is it recommended to store old metrics to frozen indices? Maybe. I will go through this, then I will go to rollups. Once I've shown you rollups, we can discuss what makes more sense for your use case. If it's some metric that you access very infrequently, maybe this is a good pattern, maybe not, because it just takes more time to access your data. You can check in the thread pool. If I have access to that, let me change that. And you can see here on that code node, I have completed 1 request against that throttled thread pool. That was that 1 operation that worked, this one here. Now, what happens if I try to add a new document to a frozen index? It will fail because one of the preconditions was that it is read-only. And now I would be curious, like, where does it even say that this is frozen? And I'm checking the settings, and I only checking like the settings that are different than the default. So what you have is, don't be confused, index provided name frozen. This is the name of the index. What you're after is this attribute here, index frozen true. So this is a frozen index, and this is how you could check that. Now, to open it up again for writing, you could unfreeze it. So here I run unfreeze, then I can run another operation, and it would just add this document append to it, and then I can just search it the normal way. But now it's not a frozen index anymore. This is a fully regular index. One other thing that I wanted to show you, let's hope that this works. So this is the dashboard of the metrics that I have collected from my containers that I have running here. And this comes back to Gregor's question, if it's a good idea to have frozen indices for your metrics. My cluster is pretty busy, so give this a moment to load. I've also never loaded this dashboard before, so there is nothing cached here. So hopefully the demo effect doesn't hit and this will load successfully. Come on, demo. My little virtual server cluster is probably struggling pretty hard right now. You will actually see that in a moment because this will show you how much or how we are doing in terms of CPU, memory, and everything on the Docker container side. If it's in a good mood, come on. Okay, I'll give this another reload. We'll get back to that hopefully after the next point. I also skip that because it's like unnecessary complication right now. Searchable snapshots will allow you to search data stored on a blob storage, which will make it even cheaper, but also potentially It's slightly slower still to access your data, but this will make it even cheaper to store and then search your data. So final point, and this is very relevant for Greg's question again, or Gregor's question around metrics. One very nice thing about metrics is that you can collect a lot of them today. Then you can pre-aggregate them as you go along. So for example, here we collect data in 10-second intervals. After a day, we roll them up into 1-minute intervals, and after a week or so, we roll them up into 1-hour intervals, because we are only interested in more coarse-grained metrics after some time. And this is what roll-ups can do. And where do I show this to you? It has a UI. I can show you the JSON. I'll go with the JSON because the JSON is always the truth. So here we have a roll-up JSON, and this is what I'm doing here. So I'm taking the data in the metric beat index. I put it into an index metric beat roll-up. I run this every minute. Might be a bit too frequent again as well, but anyway. What I'm doing here is I'm putting together 5-minute intervals of data. So I'm collecting in 10-second intervals, but now I'm aggregating 5-minute time frames together with a delay after 1 minute. So once the data is 1 minute old, I will start creating those 5-minute intervals. And I'm taking these fields, so Docker network in bytes and Docker network out bytes. You would need to specify every single field. And then I say, these are the aggregations that I want to store for them. So I take the average and the sum of network traffic in and out. So rather than storing 10-second intervals and having then 30 different data points, 5 minutes, 10-second intervals should give me 30 different data points. I'm only storing one where I have the average of this time span and the sum of the network traffic, because this, let's assume, is what we want to have. And okay, now my containers have been working, and you can see this is what I'm using in terms of CPU. So you can see, okay, my cold node is struggling with CPU usage, and the other ones are pretty busy as well. These are just the metrics that we are collecting here from our hosts. This is a pre-built dashboard. This will all be loaded when you run it. The thing that I wanted to show you here is in stack management, index management. And we want to include the roll-up indices as well. That you have here, you have a roll-up index that only contains 5 documents and 20 kilobytes of data, but this has always put together like 5-minute intervals. So this basically covers 25 minutes of data, just very compressed. I mean, of course, you will not have a 10-second interval granularity anymore, but you will get a good overview of what you have in here. So this was the final demo. If you want to get the code, this is the GitHub repository, but I would just drop the link for the slides in the chat, and then you can get the slides all together. So these are the things that we have looked at: lifecycle management, frozen indices, and rollups. And that is how you can make your cluster scale. This is what this looks like on our cloud service, where you can just say, like, give me something that has a hot and a warm node, and we will do the rest for you. That's it. That one I don't need anymore. Let me stop sharing. I will drop that in the chat. And so here we go. Panelists and all attendees, here are the slides if you want to have them. And I think I have 2 questions to answer. And do I have time for 2 questions?
Yeah, go ahead.
Okay, cool, thanks. We must create new visualizations dashboards to read new aggregation fields, or is there some workaround? Yes, so the thing that I have not shown you, or there are actually 2 things that I have not shown you around that. First off, by default, Kibana will not show you frozen indices. There is a setting in the Kibana settings where you need to activate showing data from frozen indices, otherwise it would not be shown, again, because potentially there's overhead. Secondly, for rollups, you can mix rollups and live data in one visualization. The limitation is that it will be limited to the granularity of the rollup. So if you have the live data is 10-second intervals and the rollup data is 5-minute intervals, you will only have a data point in the visualization every 5 minutes. There is a special index pattern that mixes roll-up indices and regular data, but you can mix that. It will not show up in the default visualizations, that is true, but you can build custom ones with the right index pattern in Kibana to actually show you longer timeframes. And just a side note, rollups are not a GA feature because we are reworking in the background how this is being implemented. And it will take a couple of more months potentially, and then there will be a new implementation that will look slightly differently, but have the same feature set plus some more advantages. But probably we're out of time and I don't want to dive too much into that. I hope I answered any questions. If I have more, just throw them in the chat and I can still answer stuff. Otherwise, I'm back tomorrow with another talk. If you have any questions, feel free to shoot me a message on Twitter or wherever. Thanks so much from my side for now.
Thank you, Philip, for this presentation. So Philip has one more presentation tomorrow morning, so be sure to check it out if you want to find out more about the Elastic Stack. So thank you again, Philip, and we'll continue after a short break.
Thanks for having me. Enjoy your conference day, everybody. Bye.